Reaction diffusion is a really cool and fun way to make a certain class of naturalistic patterns, and it's a great example topic for learning about what we can do with Copernicus and Houdini. Now, version 21 provides a built-in reaction diffusion solver that offers a lot of cool new features, but in this tutorial, we'll be starting from the actual math and implementing that from scratch using two different approaches. First with a node network and then with code. So in addition to seeing the pros and cons of each approach, we'll get a better understanding of how the model actually works. So before we dive in, let's do a quick overview of the non-scary math that we'll be using. Our goal is to simulate the interaction between two chemicals over time, which we will call A and B. Those range between 0 and 1, and at each time step we always start with the previous amounts for A and B and calculate their interaction in a couple ways in order to come up with the new values for the next time step. The first of these is the reaction term, which is just the amount of B squared times the amount of A. And because we're adding this to the existing B and subtracting it from A, you can think of B as being like the predator and A being the prey, or you could think of A as being like a fuel source or food, which is somehow consumed by B. But notice that if either A or B is 0, then the whole term is 0 and there's no reaction. Next up, we will add a little bit of food or fuel to our A chemical with each time step, which we're going to call F. And we're going to scale that by our existing amount of A. So if A is already at 1, then 1 minus A is 0, and that prevents us from adding any more A chemical when we're already at the maximum. And similarly for the B chemical, we're going to kill off a little bit with each time step by some amount K. And notice that we're adding K to F. So we're always going to be subtracting a little bit more from B than we are adding to A. But once again, we're scaling by the amount of B that's already there. So the more B we have already, the faster it will be reduced. And as B goes to 0, this whole term will disappear. I saved the diffusion term for last because here we have this upside down Greek letter called the nabla operator. And although it looks like it's being squared, it's actually not. That's just a concise notation for the Laplacian operator. And in a moment, I'll talk more about what that is exactly and how we can approximate it. And finally, we will multiply our diffusion values by a separate diffusion rate for the two chemicals, which for the purpose of this tutorial, we will go ahead and just set to 1.0 and 0.5 respectively. So we can think of chemical B as diffusing half as fast or half as much as chemical A. And there we have it. That's all the math we'll need, which might look a little intimidating when we see it all at once, but hopefully by building it up piece by piece, we get some intuition about what each part is actually doing. And we'll be referring back to these equations often as we put them into practice. Let's drop down a CopNet node and set its resolution to be 256 by 256, and we will leave the border mode at the default setting of wrap. And when we dive inside, we can see that same information at the top of the graph editor. Inside, we will put down a random mono and turn on random per pixel, and then we'll drop down to compare and wire into the A input of that. And since there's nothing wired into B, then whatever's coming in that's less than our comparison value is going to be turned into a white pixel, and anything else will be black. So we'll set 5% of our pixels to be white. And then we'll drop down a null node, call it in, and this will just be a convenient place where we can connect our initial condition to our simulation. While we're here, let's go ahead and make another pattern to use for debugging purposes while we're testing our simulation. So we'll drop down a stop import, dive inside, create a grid. We'll set it to 2 by 2 on the XY plane, which is the standard size of the image plane that Copernicus expects to get. And let's scatter 100 points on there, and then jump back up to the CopNet level where we drop down a stamped points node. And then we'll connect our geometry output to our points input, set our shape to be a circle, decrease the size a little bit, increase our background alpha for a solid background, and change our signature to mono, which is Copernicus terminology for a single channel floating point monochrome image. And now that we have that second pattern set up, let's go ahead and make two more nulls called A and B, which will be inputs for our two chemicals. And we will take our first pattern and invert it to be the starting condition of our A chemical. And we're set to complement by default, which means 1 minus the input, which means that wherever we have 100% of chemical A, we have 0% of chemical B, and vice versa. And with those two patterns now good to go, we can set up the main loop of our simulation, which will be contained in a block begin end. And typically you would drop down the whole block at once, but just to show you that there's another way to go about it, I'm going to start with a standalone block begin node. And we're going to set that up to have two input channels named A and B that are both set to have a mono signature. And then we'll connect our two input nulls to those inputs, A to A and B to B. And with that, we're all set to start doing the math inside of our block. Now we need to talk about convolution kernels for a moment, because that's what we'll be using to approximate the diffusion of our chemicals. When we're working with a grid of discrete inputs, like the pixels of an image, then a kernel refers to a small, fixed-size matrix of numbers or coefficients, which we can use to get a weighted combination of a pixel's value with those of its neighbors. When we multiply these values with each pixel in this little 3x3 neighborhood, add them up, and then replace the original center pixel's value with the result, that's called convolution. And by choosing different sets of kernel values, we can get a variety of different effects, depending partly on whether our coefficients sum to 0, to 1, or to something else. What the Laplacian measures is the difference between some point in our image and the average in its neighborhood. With a large difference, we would expect to see a lot of diffusion, but when our neighborhood is already diffused into a steady average, we'd expect to see no diffusion at all. So it makes some intuitive sense that our coefficients add up to 0. So these are the values that we'll be using for our simulation. And the intuition here for the -1 in the center is that all of our chemical at the current pixel is diffusing outward. And we're bringing in 20% from each side and 5% from each corner. And here's what we get when we apply our kernel to each pixel in an actual image. And notice that our kernel is wrapping around when it reaches an edge or a corner of the image. This is also going to happen in our simulation because we set the default border mode to wrap on our CopNet. Lucky for us, Copernicus provides a built-in convolve 3x3 node that we can use. And if this node is not showing up for you, just make sure that you're on the latest build of 20.5 or higher, and it should show up for you. And now we can plug in the coefficients for our Laplacian kernel, and we want to also make sure that we turn off the clamp below 0 checkbox, which is on by default since we have a -1 in our kernel. And now let's option drag to make a copy of our convolve. We'll rename it convolve B, and we'll connect it to the B input of our block begin. We can set our blue display flag anywhere in our network to preview what we're getting in either the scene view or the composite view. And in the composite view, we can zoom in all the way down to see one-to-one pixel accurate values, whereas in the scene view, we're actually looking at a shader on the geometry, which isn't necessarily as accurate. So let's take a look at our convolve B, and right away we see something doesn't look quite right. It looks a little bit asymmetrical compared to what we would expect. And as it turns out, there is a little typo in our convolve 3.3, so let's fix that, and everything's looking good. And now hit the I key to turn on the pixel inspector. We can examine our pixel values, and they should now reflect what's in our convolution kernel. So now we have our two Laplacians, and if we refer back to our actual math, we see that we need to multiply them by 1 and 0.5 respectively. And we need to make sure that we're adding in the incoming value of A and B from the previous time step. So we're dropping down a multiply constant node. And as you can see, I'm trying to give meaningful names to the nodes as I go. This is just a good professional practice to get in the habit of, even if you're not working on a team where someone else picks up your file later. Trust me that you will be grateful to your younger self when you someday return to this file and have no memory of how it was set up. So now we're multiplying our B term by 0.5. And you may also wonder why I'm bothering to multiply A by 1. You could certainly omit that node, but it's a nice little bit of future proofing just so that it's easier to experiment with that value once things are working to see what it's doing. And again, it's a good habit to be thinking ahead to what you might want to do or be asked to do in the future and kind of build with that in mind as you go. So now we're dropping down two add nodes, connecting the inputs from A and B to our Laplacian convolution kernels, and that gives us our diffusion terms for A and B. So now when we view our diffusion term, we have an error. So let's middle mouse on that, see what our message is. Source is missing. That is because I accidentally wired to the wrong input. Problem solved. And now if we look at our diffusion term, again, something looks not quite right. And that is because we copied and pasted our typo from our first node. And now everything is looking good. And I changed my mind on these node names, so I'm just going to refine them a bit. But hopefully by not editing out these mistakes, you can see one advantage of this approach, which is that we can visually debug step by step, node by node as we go. Let's move on to our reaction term, which is b squared times a. Now to get b squared, we can drop down a function node. We can set its function type to power with an exponent of 2. Or we could just drop down a multiply, and we could wire b into both inputs to multiply it by itself. So let's go ahead and use that second approach. And then we will drop down one more multiply and connect a to one input and b squared to the other, which is all we need for our reaction term. And now we can set our display flag anywhere we want in our network to understand what's going on at any particular node. And if we inspect the values of our reaction term, for example, we can see that it's all black, which makes sense because our input pattern currently has no pixels that overlap the two chemicals, so they're always going to multiply to 0. So let's switch to our other pattern that we made earlier, and we can go ahead and make those circles a little bit bigger. And now we see something going on in both the diffusion term and the reaction term. And again, this is because we're instancing these circles, which are anti-aliased, and so there are grayscale values around the edges where the two chemicals are now overlapping. Okay, so let's switch back to our original pattern for our initial condition. And next we need to make sure that our reaction term is being added to our B chemical, but subtracted from our A chemical. And the only trick here is that we need to be aware that the subtract node subtracts the foreground from the background. So unlike with the add node, the order of the input connections does matter, and we want to make sure that the reaction term is connected to the FG input. And by the way, the reason that the inputs are labeled that way is because when you drop down an add or a subtract, what you're really doing is making a blend node with the blend mode already preset appropriately. And now to start setting up our feed and kill terms, we'll drop down a constant node and set it to 0.035. Drop down another one for our kill term and set that to 0.058. And these are values that I borrowed from another tutorial that I know will give us an interesting result. And if we refer back to our equations now, we'll remember that we need to scale the feed term by 1 minus a, and we need to scale feed plus kill by b. So let's start by dropping down an invert. And again, that is in complement mode by default, which gives us 1 minus a. And now we need a multiply node to which we connect our feed and our 1 minus a, which gives us our feed term. And likewise for our B chemical, we'll drop down an add node to add up our feed and our kill, give that a name, drop down another multiply node to scale that result by our incoming B value. And I think now we're starting to get a sense of maybe one of the downsides of this approach, which is that this is a lot of tedious manual wiring for some pretty simple operations. And that can be error prone and also possibly take more time for someone else who's looking at your file later to understand what's going on. But we're almost done. So let's press on and drop down an add node to add our feed term to our A chemical and a subtract node to subtract our kill term from our B chemical. And again, with our subtraction, we want to take care that we're connecting the incoming sum to the background input and the kill term to the foreground input. And with that, we're all done with the math that we need to do at each time step. And we are ready to wrap that up inside of a block so that we can now loop over it for our simulation. So let's drop down a block end node, and we are going to give that 2 outputs, which will match the names of our inputs, called A and B, both with a mono signature. And then we'll connect the outputs from our network into the inputs of that node. And with our block end node still selected, we can Control-C or Command-C on Mac OS and paste that into the block path of the block begin node. And now we see this highlighted convex hole around everything that's contained inside our block. Now we're ready to loop over our block by dropping down an invoke block and pasting in that same end path. And by clicking this button, we automatically set up our inputs and outputs with the correct signatures. And now we can connect our input patterns to the A and B inputs of our invoke block, and we should see the exact same result that we get from the block network. But the advantage of using an invoke block is that it provides an iteration slider, which will take the output of the block and feed it back to the inputs as many times as we want. So as we turn this up, we start to see our simulation evolve. And as we push our iterations even higher, we start to see the classic features of a reaction-diffusion pattern emerging, which is super cool. And by the way, in version 21 and higher, you wouldn't necessarily do it this way anymore, as there have been some new simulation features that were added to the block itself. But it's still good to know that this is an option. You can see that our cook time is getting less interactive as our iteration counts are getting higher and higher. For example, if we try 1,000 iterations, I'll cut this out of the video, but this took about 7 or 8 seconds in actual time. And let's see what happens with 4,000. I'm going to speed this up by 10x in the video, but we can see that after about 30 seconds, there's still a slight evolution in our pattern. And just for fun, let's try plugging in our other input pattern. And again, I'll speed up the recording by 10x, and as you'd expect, we get a slightly different result. So far, we've been looking at the A output, but for any Copernicus node, we can see whichever output we want using this pop-up in the corner, which works for both the thumbnail and the scene view. And for the composite view, we can do the same thing using this pop-up in the toolbar of the viewer. And now we can start to get creative and experiment with the many other nodes that Copernicus offers for image manipulation. For example, we could combine the two outputs in some way, or let's try connecting our B output into a mono to RGB node so that we can apply a color ramp to that. And we can see that our B values are kind of clustered around the low end, so let's try using A instead. And now we're getting a wider range of values, but I'm curious if we turn up our iteration count by another factor of 10, what happens? So this is sped up by 20 times, but we'll see that after about 90 seconds, there's a small change, but it seems like our A values have kind of settled into this central range. And this would be a good point to pause the video and do a little experimentation of your own. You might try using an equalize node, going into a mono to RGB, and see what happens when you add more knots to the ramp, and just experiment until you come up with something that you think looks cool. And before we move on to part 2, I wanted to mention one more debugging tip. If you want to inspect what's going on in the simulation at some later point, we can change our invoke block to whatever point we're interested in. So let's say 10. And now by option dragging the entire block network to make a temporary copy, we can now connect the outputs of our invoke block, which has already simulated 10 steps, into the inputs of this new copy of our network so that we can visually inspect what's going on at any node between the 10th and the 11th steps of our simulation. In our second approach to simulating reaction diffusion, we're going to be replacing most of our node network with a snippet of OpenCL code. Back up at the object level, let's option drag a copy of our CopNet from part 1, rename it OpenCL, and dive inside. Let's select and delete everything inside our block except for our 2 convolve nodes, and cut the wire between the block begin and end by holding down the Y key and dragging across it. And then we'll just delete a few nodes we don't need to clean up, and drop down an OpenCL node. The first tab in our OpenCL parameters is the kernel code, which again is just a function that runs over every pixel in your image. And there's some default code that just takes the input to the output, and the signature tab is where we tell Houdini what types of inputs and outputs to expect. And there's a pop-up menu that provides a few snippets of example code that we can refer to. So we'll start by deleting the default code and start to declare our own bindings using this hash bind syntax, which is a shortcut that's provided by side effects to help simplify writing this code. And float just means a floating point number, which is equivalent to a mono signature in our network. And we're going to create 2 layers called A and B, which are both readable and writable, since, as before, we want to use our outputs and feed them back to the inputs of the next time step. And we'll create 2 more input layers where we can connect our convolve nodes. And these can be marked as read, no write, because we're using them only as inputs, but we're not writing data back out to them again. And lastly, we'll create 2 more layers for our feed and kill terms. But in this case, since we don't necessarily want to connect an input to them, we can mark these layers as read, no write, optional. And because they're optional, we now have to provide a default value, which will get used whenever there's nothing connected. And so we'll just use the same exact numbers that we used in part 1. And by the way, there is a more concise syntax for all of these layer binding options that's described in the documentation for the OpenCL node. And now we're ready to actually write our kernel code. And because we use the reaction term twice, we're going to put that in a variable. And we use this @ syntax to refer to our inputs. And that syntax, along with the @kernel and this @set macro, are another shortcut that SideVex has provided, which greatly simplifies and reduces the amount of code that we need to write here. And now it's just a matter of translating our equations into code. And again, for each of our inputs, we need to use the @sign, but we don't need to use it for the reaction variable that we declared. And if you're brand new to programming in general, I'll just mention that these parentheses are required in order for the subtraction to happen before the multiplication. And the f after the 1.0 and the 0.5 is required for floating point numbers in OpenCL. And lastly, the parentheses around feed plus kill are also required in order to correctly match what our equation is doing. So that's it for our code. And now we just need to update the signature to match, which still has the source and dest left over from the default code. And we can do that automatically just by clicking this button. But if you hover over it, you'll see the help text is telling us that we can control click to fully rebuild. And that in fact is what we want to do in this case, so that we get rid of the source and dest and replace them with our own inputs and outputs. And now we can connect from A to A and B to B, and hook up our two convolve nodes to our diffusion inputs. And then we'll wire the outputs from our OpenCL into our block end. And so far that's looking pretty good. So if we go to our block invoke now and start to crank up our iteration count, we start to see our pattern emerge. And we also notice that things are running much faster than before. And we're getting closer to interactive frame rates even with high iterations. So let's try doing 4,000 iterations, which was taking about 30 seconds with our network approach. And we'll let this run in real time. And that took about 4 or 5 seconds. So let's try 10,000. That was running at 90 seconds before. And let's see what we get now if we'll just let this run in real time again. And about 11 or 12 seconds. So it's a pretty dramatic speed up. Let's change our iterations back to 1,000, and let's do one more debugging step just to confirm that we're getting the exact same result from both approaches. So I dropped down a null here and named it out. And we're going to go back up level, dive into our original node network approach, and we will set our iteration count to 1,000 here as well. And now we can jump through a little hoop to compare the results side by side. Put down a SOP import, dive inside, create a copnet, turn on use external cop, and point it to the out null that we just created in our other copnet. And now we can jump back up and connect our SOP import to a geometry to layer node and make sure that that has an RGB signature. And now we can use our display flag to compare the results directly side by side and confirm that we're getting identical results from both approaches. Let's dive back into our OpenCL version now to just confirm that we're getting seamless tiling across the edges. Now, if we look at our input pattern, our scattered points are definitely not going to tile seamlessly unless we had taken steps to make that happen. So let's switch back to our original pattern of single random pixels. To confirm that our resulting reaction diffusion pattern is seamless, we could normally go back to the scene view and just turn on this tile viz checkbox to see a 3x3 layout. But for whatever reason, that doesn't seem to be working here. So we may have hit a little bug, and we're going to try it a different way. Let's drop down a preview material and wire our output into the base color, and then change our shape to be a torus. And everything's looking great. Looks like our pattern is perfectly seamless across the edges of the texture. This is all super satisfying, but Copernicus looks unimpressed, and the reason is that half the fun of reaction diffusion is watching the pattern emerge over time. And right now, all of that evolution is hidden away inside our invoke block. So let's look at one way we can render animations while still using this approach. Again, in version 21, this is all much easier, but there are a couple of tricks we can learn that are still generally useful. Let's take a look at the setup for the animation you just saw. So here we're bringing in an image from disk, downsampling it a bit, and then using a fractal noise into a slope direction to add a little distortion. So here's before and after. And that is our initial condition, which we're splitting out into A and B with one side inverted, just like before, which is feeding into our reaction diffusion block using OpenCL this time, as well as into an invoke block. And here we're using 3,600 iterations to complete our simulation, which is taking about 20 seconds to cook for an image this size. From there, we're developing two different looks. First, just applying a color ramp, and secondly, using a segment by connectivity, feeding into a random mono, and then into a similar color ramp. And these two looks can then be rendered out as separate image sequences using these ROP image output nodes. Now we could drive our iteration count with an expression based on the frame number. The problem is that invoke block always starts from the beginning, so our cook times are going to get longer and longer as our animation progresses. Instead, we need to start our simulation from the point where the previous frame left off, which we can do by simulating a few steps at a time. In this case, we'll choose 4, and then writing out our A and B values to disk using an additional ROP image output. And now when we drag our invoke block into our cop path, we see an edge with an arrow linking the 2 nodes. And now we're going to paste in a path to an EXR file. The advantage of using EXR is that we can save both of our outputs to a single file by creating 2 output AOVs, which we'll name A and B. And then we can use a file node to read the image back in, pasting in the exact same image path we used before, and again creating 2 input AOVs called A and B. And these both need to be set to have a mono signature. And now we can connect the output from our file read to replace the output previously coming from our invoke block. And with the file node still selected, let's Command-C or Control-C so that we can paste a copy of it up at the top of the network. And now we need to do a little rewiring to take advantage of that file read. So let's delete our input null and make some room after our invert node to drop down a switch, which is going to feed into our A input. And on the selector for the switch, we will put in an expression, which is $F greater than 1. So when this is true, at any frame larger than 1, it's going to switch to the second input. Now let's option drag our switch to make a copy, and we'll connect that to the uninverted image that we need to be using at frame 1, and that will be connected to our input B. Now we'll rename that switch B, and that has the same expression that we have on switch A. And now we just need to connect the A and B outputs from our file read into the second input of both switches, A to A and B to B. And now at frames 2 and above, this file node will be what's read. And all we need to do now is modify the expression so that we're reading from the previous frame instead of the current frame. To make our lives easier, let's edit the parameter interface and add a spare string parameter right above the file name. And we'll call that previous frame. And we're going to put an expression on this parameter to give us the previous frame number. And I think the easiest way to do that is to right-click, go to Edit String, and then change the pop-up at the bottom to Python expression. And so we'll take our integer frame number, subtract 1 from that, convert it to a string, and then format it with zeros. And that looks perfect. Now we've got 1 frame less than whatever's set in our timeline. And the last thing we need to do is to plug that value into our file name expression by replacing our $F4 with a backticks containing a channel string for the previous frame parameter. And there's one last detail to take care of back on our ROP image output where we're writing out our A and B values. We need to go to render settings and turn off save in background. And this makes sure that when we're rendering the whole frame range that each frame writes out completely to disk before the next frame tries to read it in. And with that, we're ready to kick off the full frame range with a constant cook time per frame. And once that completes, we can kick off the renders for our final looks. Thank you so much for listening. I hope you found this interesting. If you did, please give the video a like and let me know in the comments if there's any topics you'd like to see covered in future videos. And by the way, you can imagine my reaction when I learned that it was actually Dr. Alan Turing who pioneered this whole field of study back in the early 50s when he wasn't busy inventing computer science.